So welcome everyone to today's colloquium. Today we have a real treat for you. Our speaker is Katelin Schutz, formerly our own brilliant graduate student, now a Papalardo and Einstein Fellow at MIT. Katelin finished her PhD in 2019 with Hitoshi Murayama, working on the search for the invisible, working at the interface between particle physics, particle theory, astrophysics, and cosmology, using observational, cosmological, and astrophysical data to illuminate the dark sectors of beyond the standard model physics. Her thesis was so successful that she actually received the Sakurai Dissertation Award from APS, then moved on to these two fancy fellowships at MIT, and this summer she will be starting as an assistant professor at McGill University. So she is definitely a rising star in physics. She collected all kinds of fancy fellowships during her graduate years, including our own Brantley Fellowship. And that goes every year to the best BCTP graduate student. And she has been on a stellar trajectory. You can see that trajectory, not just by taking me by my word, but also noticing that she has received the official Rising Star in Physics award by MIT and Stanford physics departments. So it's a real pleasure to welcome her, and please, Katelin.
Wow, well, thanks so much for the really kind introduction, Petter. It's a real pleasure for me to be here today. This feels like a real full circle moment to be back at my alma mater, if virtually. And today it's my pleasure to tell you about this fascinating idea for potentially explaining the origins of dark matter in our universe, making dark matter out of light. Now, that's something that at face value might sound kind of paradoxical. How can you make dark matter out of light? This makes no sense. But my hope is that by the end of this colloquium, you'll take away from it that this is actually a highly self-consistent theory of making dark matter in the early universe. And it's one that is immediately testable using techniques in the lab, as well as using astrophysical and cosmological observables. And during the course of my talk today, I'm going to be focusing primarily on the latter and taking you on a little tour of all of the different kinds of astrophysical systems that inform our understanding of dark matter. Before I get started, I want to acknowledge my really excellent collaborators, Cor Dvorkin and Tongyan Lin, who've been working with me on this idea. You can read more of the details about this work at these references here if you want to take a look after the colloquium. Okay, so let me get started, and I just want to do some quick housekeeping and make sure that we are all on the same page about the following statement, namely that dark matter exists and is dark. Now, we have great astrophysical evidence for this statement, and I'll go into that in the next few slides. But I want to also note that I put an asterisk on the word dark here because from a purely observational standpoint, this is something that we can only ever put a bound on from above, right? So saying that dark matter is dark is kind of an assumption. And until we actually discover what the dark matter definitively is, it's just that it's only an assumption. And as we'll see in this talk, it's possible for dark matter to be just a little bit not dark and still have a compelling origin story. Okay, but just to kind of quickly recap some of the systems where we see great evidence for this statement, let me first start with one of my favorite pieces of evidence, which is merging galaxy clusters. So what you're looking at here is a picture of the Bullet cluster. It's one of the most famous examples of merging galaxy clusters. And what you're looking at is the remnants of two clusters of galaxies that have ripped through each other. And we're seeing sort of the aftermaths after this has occurred. Now, what you're looking at is actually a composite image. So on the one hand, you see these kind of blue blobs, and what those represent are where most of the mass is located in this plane. And that's inferred using a technique called gravitational lensing, where we're basically looking at the correlated shapes of galaxies in the background, which are being very subtly lensed by foreground mass. And based on how those images are distorted, we can infer that most of the mass in this picture is in these blue regions. At the same time, in pink, you're seeing the normal matter using X-ray telescopes like Chandra Space Telescope. And the normal matter gets very, very hot because what's happened here is, right, this is the aftermath of a merger. These two galaxy clusters have ripped together at roughly 1% the speed of light. So that's very fast, very supersonic relative to what's going on with this ordinary matter. And what's happened is that it's basically thermally emitting X-rays because you have this merger And because ordinary matter is able to scatter on a particle by particle basis, it's able to exchange energy and momentum on a particle by particle basis, you're able to convert some of that bulk gravitational motion into thermal motion and into drag. So you're able to not only heat up this ordinary matter, but also slow it down. So these two clouds of baryons are exerting a force on each other, and that is why they're slowed down relative to what the blue regions represent. So the ordinary matter gets slowed down because it feels a drag force, but whatever's making up these blue regions does not feel that same drag force. And so this kind of a picture is really great evidence for the statement that there's some kind of matter that doesn't behave like ordinary matter, doesn't have particle by particle scattering, exchanging energy and momentum. And we also know that, if dark matter has interactions, they are very bounded by this picture. Moving to larger scales, if we look at the cosmic web of large scale structure that we observe in our universe, we observe that things on very large scales look actually quite clumpy. And it turns out that things don't cluster as well when they're made only of baryons. And that's largely due to the fact that baryons have a harder time collapsing in the early universe. And I think that those kinds of initial conditions are also easily seen going to even larger scales, looking at the cosmic microwave background. And I'll go into this more later in my talk, but essentially what you're looking at here is the afterglow of the first roughly 300,000 years after our Big Bang, where we had this primordial plasma comprised of photons and baryons, which was trying to collapse, but because it was a tightly coupled plasma, radiation pressure prevents the baryons from collapsing down. And based on studying how this plasma is behaving, we have evidence for some component of matter which does not seem to feel radiation pressure. It seems to be able to collapse down at earlier times. So all of that evidence, and there's other pieces of evidence as well, but with all of that evidence, naturally we want to know, well, what is this stuff? It seems to not really be behaving like ordinary matter. And so what are its properties? What is it made of? Where did it come from? That's kind of the questions that we want to get to as, I'm a particle physicist, so that's really what I care about. Now, from a purely empirical standpoint, we don't really know very much about this question. We don't really know very much about what is the dark matter. Let me just illustrate our relative ignorance by just focusing in on one parameter. So if I focus on the mass of dark matter, if I assume dark matter is one thing and it's, it can have any mass it wants, it turns out that observations constrain the mass of dark matter to be within 90 orders of magnitude. So that's a huge, huge range of possible masses that dark matter can have. And over 90 orders of magnitude, naturally, you're going to have qualitatively different kinds of dark matter behavior. So here I'm schematically showing different kinds of dark matter theories, ranging all the way from the very high mass end, where you have dark matter not even necessarily being made of new particles, but perhaps compact objects like primordial black holes. Moving down in mass, we have composite dark matter, WIMPs, we have the light dark sectors, and then going even further down in mass, we get into a regime where dark matter is very, very light. It's made of bosonic fields, and it's oscillating and behaving like a wave on length scales that are observable in astrophysics and cosmology. And so that's kind of what bookends this range of masses here. And this is a huge range, right? So there's a lot to understand here and to really unpack in more detail. Now, for those who maybe haven't really been following this story too much, you might be wondering, well, why do I need this 90 orders of magnitude? Why can't I just focus on, the best dark matter candidates? So, for example, weakly interacting massive particles, WIMPs, are one of the most canonical examples of a dark matter candidate. It's the example that we print in textbooks, for example, and tell the public about in outreach talks, for example. And so you might be wondering, well, why do we need to focus on this 90 orders of magnitude? What's the status of WIMPs? And so I want to really briefly, review this and just motivate thinking about the broader picture of dark matter and all the different possibilities. So quickly, just to review what's going on with WIMPs. WIMPs are a thermal dark matter candidate, and they're born through a mechanism called freeze out. So let me just tell you how that works. So what's happening in this plot is that I'm plotting the density of dark matter, but I'm plotting the co-moving density. So I'm factoring out the fact that the universe is expanding. So I'm factoring out that volume factor. And at very, very early times, at high temperatures, when the temperature of the universe is higher than the mass of this particle, then it's a relativistic particle. And on dimensional grounds, its number density has to scale like temperature cubed. And because temperature is inversely proportional to the length of our universe, that means that at early times it has a constant co-moving density. However, this behavior cannot persist because as the universe expands and it cools down, if the temperature drops below the mass of this particle, then you're going to start having a Boltzmann suppression, e to the minus mass over temperature, which means that if there is some sort of process that can deplete the dark matter density, such as the one I'm schematically showing in the bottom, where you have dark matter particles annihilating to standard model particles, if you have such a process that's active, then you're going to ride this exponential Boltzmann curve down and you're going to deplete the number density of dark matter. But also this phase cannot persist forever, because at some point, you've depleted the dark matter number density so much that these dark matter particles have a hard time finding each other in order to annihilate. So at some point, this annihilation process becomes really inefficient because there are just so few particles to annihilate and find each other. So at that point in time, what happens is that the amount of dark matter becomes constant once again. And it turns out that if you plug in a weak scale mass and a weak scale cross section to this process, then the amount of dark matter that you end up with at the end of the day is actually remarkably, very similar to the amount of dark matter that we observe in our universe. And that is kind of crazy because on the one hand, you're taking a known scale in physics, you're taking the weak scale, plugging it into this, thermal process, which you didn't tune any knobs or dial any knobs, and then out pops a number that you observe in our universe that we have no a priori knowledge of, right? So this is deductive reasoning here. And so the fact that this is, this is lining up is a huge coincidence. There's a name for this, actually. It's called the Wimp Miracle. And this is why, WIMPs have been such a big focus of the search for dark matter. This is one of the most compelling reasons. And it didn't have to be this way, by the way. These different shaded bands correspond to, had I changed one of those parameters by an order of magnitude, the amount of dark matter would have also changed by an order of magnitude. So this is really crazy. And on top of this, the WIMPs have another nice property, a few other nice properties, namely that the relic abundance is independent of initial conditions, didn't have to tune anything. So that's a good property to have. This process is fine with early universe observables, provided that dark matter is heavier than a few MeV. More on that point later. And then finally, a really nice thing about this is that the relevant couplings are small, but they actually can be experimentally probed. And there's a whole rich program to try to discover these WIMPs. Ironically, I think the most direct way of looking for WIMPs is through indirect detection, which is a process where you look for this kind of annihilation process, dark matter coming in and annihilating to standard model particles, which you then try to detect, for example, with gamma ray telescopes and neutrino telescopes. And the reason why this is the most direct way of looking for dark matter is because it's the exact same process that was setting the relic abundance in the early universe. So based on the requirements that we get the amount of dark matter that we observe in our universe, you have a very tight prediction a dashed line on this plot. So that's a really nice concrete prediction. If you're above that line, you have not enough dark matter. If you're below that line, you make too much dark matter. Now this parameter space is constrained on the low mass end by searches for annihilation to visible products. At the same time, you have a constraint from the high mass end from partial wave unitarity. So you're really left with this very finite window of masses where WIMPs could be all of the dark matter for like 10 GeV and above. And the prospects for closing this window with indirect detection are rather futuristic, so it's probably not going to happen in the near future, but that's okay because we have other ways of looking for WIMPs, one of them being through direct detection, which is an alternate strategy where you look for dark matter particles coming into the lab, scattering off of some sort of target that's from the standard model, and then you look for that recoil. And there are a number of different kinds of experiments doing this. Here I'm showing an adapted plot from the 2013 SNOWMAS report, so it's several years out of date now. But I think this plot is great because it just shows the diversity of experiments that are all doing this. And many of these dashed lines, which were projections at the time, have now been filled in and have now actually excluded much of this parameter space. So these experiments have been highly successful at working exactly to spec. At the same time, though, it's a little disappointing because we still haven't found the dark matter. Now, that doesn't necessarily mean that WIMPs aren't dark matter, because there is some degree of model dependence between how you equate annihilation in the early universe and scattering on standard model particles in the lab. So unlike with indirect detection, where it's the same type of process, here we have some model dependence. And so it's a little bit unsatisfying because it could be that, WIMPs are all the dark matter, but, their coupling to nucleons is just very suppressed. Or it's possible that WIMPs aren't the dark matter, but we don't really know one way or the other right now. We're going to just have to wait for more data. But in the meantime, I think this, really motivates thinking about alternatives to WIMPs. And so I think going beyond the WIMP paradigm, now is a great time to do that. And there are a few other reasons why I think that's true. First of all, the WIMP was only one example of a thermal scenario. As we'll see during my talk, I'm going to talk about an alternate example. And the emergence of the weak scale could have just been a coincidence, right? So it's a pretty big coincidence, but that's not unprecedented in the history of particle physics. For example, as my advisor Hitoshi taught me when I took his standard model course, Rabi famously said, who ordered the muon? Because when the muon was first discovered, it had many of the same properties as pions. And so people thought the muon had something to do with the strong force. And of course, nowadays we know that the muon is just a heavy electron. It has nothing to do with that. And it was all a big coincidence, a big misunderstanding. And so that could also be what's happening with dark matter as well. Moreover, the standard model is not minimal, right? We have all these particles interactions that give us things like galaxies and planets and humans and ice cream, right? So it's also possible that the dark matter has a similar level of complexity, and maybe that wouldn't be too surprising. And finally, one thing that I find especially compelling is that we're going to have a lot of new technologies and new kinds of qualitatively different observations, which are going to allow us to probe different kinds of models of dark matter. And so we had better be ready for these new observations and new technologies. So big picture, here's how I like to think about it. Here's how I like to think about the standard model. We have this Venn diagram of all the different particles and the forces that they feel. Of course, with gravity being the outermost bubble of this Venn diagram, because gravity has this amazing property that we think to good approximation, it's universal. And that wonderful fact has allowed us to discover this new component of matter, which we call dark matter. And given everything that I just said, it's highly conceivable that dark matter has its own complexity, maybe its own associated other particles or other forces. So I can schematically draw the dark matter as being part of its own Venn diagram. And if that's the case, then maybe that sector directly talks to particles in the standard model. Maybe there's some overlap in this Venn diagram. And if that's the case, then that's actually very convenient because we can use that Venn diagram to actually use a direct portal to probe what's going on inside of this new sector. And here are a couple of examples from my work. In the same time, you could be really pessimistic. You could say, well, what if this component, this sector was totally decoupled? What if I take away all the direct couplings to particles that we know about? But again, the fact that gravity is universal means that at the very minimum, you have a gravitational portal to this sector, and you can actually still use gravity to learn about what's going on with this new force. And again, here are some examples from my work. Now, the focus of today is going to be on sort of an intermediate case where the dark matter is going to couple at a very small level to regular particles, but gravity is just so powerful and we have so much measurements and information about what's going on that gravity is going to turn out to be the most efficient way of learning about what's happening here. So to go back to my big schematic plot of what the dark matter is doing, today we're going to focus on the keV to MeV mass scale, which as we'll see is kind of a special mass scale. And we're going to deep dive on different astrophysical systems and the diversity of them that can probe dark matter in this mass range. So without further ado, let me tell you about making dark matter out of light. And this is going to be, as we'll see, an example of freeze-in. It's a thermal-ish scenario, and that'll become clear soon. I want to also note freeze-in, this is not something that's new. This idea was actually pioneered, for instance, by people at Berkeley like Lawrence Hall. But what's happening here when you make dark matter out of light is as follows. So it turns out that inside of a very dense, very conductive medium, photons effectively have an in-medium mass, a plasma mass, and they get promoted to what are called plasmons. And in other words, they have altered dispersion relations. They don't have this nice gapless dispersion relation, they actually have a gap. And because they have these altered dispersion relations, whereas in a vacuum, photons can't decay because there's zero phase space available, suddenly now inside of a medium, there's tons of phase space available for decays, provided that the decay products are sufficiently light and sufficiently weakly coupled to the plasma. And this might sound very exotic to you. It did certainly to me when I first learned about this, but it turns out that this kind of process happens all the time in the standard model. So let me just give you a concrete example of that by plotting the white dwarf luminosity function. So what this is just counting how many white dwarfs are there as a function of their intrinsic brightness. So the left side of this plot is the brighter, hotter end. The right side is the dimmer, cooler end. And white dwarfs are a relatively simple star. So the very spherical cow understanding of how they work is that they're born quite hot, and over time they cool down. So they start out on the left side of this plot and they move towards the right over time. Now what's shown here in purple is data. At the same time, the blue is the results of a stellar evolution code, and it seems to be agreeing very well with data. Now what this orange line is showing is it's showing surface photon cooling. So white dwarf stars are not very good at emitting photons from their entire volume because white dwarfs are very, very dense. They're held up by electron degeneracy pressure. So there's tons and tons of very densely packed electrons. And so photons trying to leave from the interior of the star are not able to escape because there's just too many electrons that are blocking them. But they are efficient at cooling down from the surface, so they can cool down that way. And that kind of cooling law is actually a fairly good prediction for many of the intermediate magnitudes shown here. So this orange line seems to be matching up fairly well with the purple dots for a large range of magnitudes. However, there's this very noticeable dip at the very hot end, and what's going on there is that there's this extra process that you have to account for, which is that these plasmons can decay to a pair of neutrinos through an electron loop. And what that does is the effect that has is it means that there's an additional cooling channel for stars to cool down more rapidly, which means that they evolve from the left to the right more quickly than they would have otherwise. So there's fewer very, very hot stars because they just cool down so quickly. So this is actually a well studied phenomenon in stellar astrophysics. And me and my collaborators were looking into this for other reasons, but we looked at plots like these ones and we thought, well, it seems like these plasmons are especially very efficient for very, very hot stars. And why wouldn't that also be true in the early universe, right? Because the early universe is also a very, very hot, very, very dense plasma. And it turns out that that was right on the money. And it turns out that dark matter can be made very, very efficiently this way, particularly if the dark matter is lighter than an MeV. And as far as I know, it's one of the most efficient ways of making dark matter in the early universe, just because our universe has so many photons in it. Now, it's actually so efficient that you have to really make sure that the coupling between dark matter and this photon is very, very small. So how might you accomplish that? Well, one example that you could have to accomplish this is, well, maybe dark matter lives in its own little bubble. Maybe it has its own dark matter version of E and M, complete with a dark matter photon. And at some level, that dark photon will mix quantum mechanically with the ordinary standard model photon at some very small level. If you want to think about it like neutrino oscillations, that's maybe one way to think about it. It's not a perfect analogy, but you can think about it that way if you'd like. And this type of situation, by the way, this is one way to achieve this coupling. It's not the only way, but it's a particularly nice one because these kinds of theories where you have this hidden, U1 happens a lot of the time in certain kinds of string theories. So that's kind of interesting. Another really interesting thing about this scenario is that as far as I know, this is the simplest way of making dark matter that has a small effective charge. In other words, dark matter that is effectively not dark. For example, if you tried to make dark matter through freeze out, the process that I talked about before where we were making WIMPs, that would actually not work because dark matter would not be sufficiently dark to be consistent with what we've observed the properties of dark matter to be. So that is very, very ruled out. So this is, as far as I know, the most simple way of making dark matter with a small effective charge. So that's all very interesting. Now I want to talk a little bit more about the sort of thermal history of how this dark matter gets made and compare and contrast a little bit with WIMPs. So let me just briefly do that. Again, I'm going to plot the number density of dark matter, but I'm factoring out the relic density. So that's a quantity that is a co-moving quantity. And by the way, I think this plot looks like a dolphin. So here is the eye of the dolphin, just to help you see it. I call this the dolphin plot. So what you're seeing here is very similar to what I showed you for the WIMP case, the weakly interacting massive particle case, several slides ago. However, I'm plotting a dark matter mass of 1 MeV this time, so way, way lighter than the weak scale. And you see the similar thing, right? It starts constant, it goes down, it's Boltzmann suppressed, and then it's constant again. However, in this case, because the dark matter mass is so light, this process is happening at a very important time in our universe. And it's actually excluded for the following reason. So while the number density of dark matter is being depleted at this time, you're going to transfer substantial energy and entropy to the visible sector through these annihilations. So you're going to heat up the visible sector. And that is bad because if you do that, then, first of all, at a temperature of roughly 3 MeV, the neutrinos decouple from the thermal bath. And so if you heat up the visible sector, then the neutrinos are going to have a weird temperature compared to the visible sector. And that's very not good because that's one of the most well-measured quantities in cosmology. At the same time, if you are injecting a lot of energy into the visible sector, you also have the potential to mess up the formation of deuterium, which is one of the stepping stones to building up the light elements during nucleosynthesis in the Big Bang. So we need both of these things to happen in order to be consistent with observation. So that's why this kind of dark matter mass, this freeze out process is excluded. And that's sometimes why, for the experts in the audience, you will hear people say that you can't have thermal dark matter below an MeV. However, what you'll notice is that in blue, I'm showing the line for freeze-in. And you'll notice that the density of freeze-in dark matter particles is way lower. And that's because freeze-in dark matter actually never thermalizes. It never has a thermal number density. So as opposed to the freeze out case where you have this very high number density and then drop it, the reverse is true for freeze in. You start with very little dark matter and you make more and more over time, with the dominant contribution to the dark matter being made at the latest possible times. And because you never have very many particles, you never have very much energy or entropy in this sector, that means that you don't have any of these issues that I just told you about. And so that's why freeze in is kind of a unique way of making dark matter in the keV to MeV mass range, because it's thermal-ish. So it's being made from the thermal plasma, but the dark matter itself is not thermal. So that's very crucial. Now, for some of you, who have a more experimental mindset, you might be wondering, well, if you're making the dark matter so weakly coupled that it's never thermalizing, then how are we going to detect this thing, right? How is this going to ever be something that we can try to measure? It turns out that the very light mediator saves us in this case. So it's true that just because the dark matter is not in thermal equilibrium, that does mean that the coupling must be tiny. However, anytime you have scattering via a light mediator, for example, this light dark photon, naturally that's going to have a velocity to the -4 cross section. And that's the same thing as what happens in the standard model with Rutherford scattering. And that's actually a really powerful, very steep scaling. So, in the early universe, things are relativistic, right? So things are going roughly at the speed of light. But today in our galaxy, the typical speed is of order 10 to the -3 times the speed of light. So that's potentially 12 orders of magnitude of enhancement to the cross section, which is very, very powerful from the point of view of a direct detection experiment. So as to whether you can test this thing in the lab, the answer is maybe, with some upcoming future technologies. If I plot the effective charge that you would need to make this dark matter this way as a function of dark matter mass, then indeed the purple line is showing you what the effective charge would have to be. And it's really tiny. It's 10 to the -10 or 10 to the -11. But at the same time, there are all these different constraints that can come in here. First of all, on the very low mass end, we have constraints coming from stellar emission. And that's very similar to what I told you about earlier, where you could make dark matter in the cores of stars and cool them down too quickly. And then they would have properties that differ from what we observe. So that's actually excluded on the low mass end. At the same time, you see all these dotted lines, which all correspond to proposed direct detection experiments. Actually, these were proposed at Berkeley. And all of these kinds of experiments are making use of the fact that certain materials have a gap, which is very kinematically well matched to the kinematics of low mass dark matter coming in. So freeze in is one of the main targets of these various proposed direct detection experiments, pretty much for the reasons that I just told you about, right? So freeze in is kind of a unique way of making dark matter below an MeV through some sort of thermal process and having some predictive way that you can map it onto direct detection. So freeze in is a really important benchmark for these different proposed experiments. So at this point of the talk, I want to just quickly recap what I've said so far before I move on to talking about cosmology. So quick recap of the particle side so far. We talked about thermal freeze out, where we saw that if dark matter is made through annihilations to standard model particles, then the relic abundance was independent of initial conditions, of things happening at very early times, fine with early universe observables, provided that the dark matter is heavier than a few MeV, and the relevant couplings can be experimentally probed. And now if I take this schematic blob of a diagram and just reverse the time axis, that gives me thermal freeze in. And specifically, if we look at this channel of making dark matter through this plasmon decay process, making dark matter out of light, then you have a lot of the same nice properties. So first of all, the relic abundance that you get is independent of initial conditions because most of the dark matter is made at very late times, very low temperatures, so you're not sensitive to the UV physics. This is fine with BBN and effective, uniquely in the keV to MeV mass range. And indeed, the relevant couplings, even though they're very, very tiny, can be experimentally probed. So now for the remainder of my talk, I want to discuss how to constrain the situation with cosmology. So Yakov Zoldovich called our universe the poor man's accelerator, poor man's particle physics experiment, and so that's how we're going to be treating it for the rest of this talk. And the key insight that we're going to be using to do that is the fact that dark matter is born hot from this process of freezing. And here hot is in quotation marks, because as I've tried to emphasize, the dark matter does not thermalize. It does not necessarily even possess a well-defined notion of a temperature. And so it's not really fair to say that it's hot. However, when I say hot here, what I mean is that you have dark matter that's being made from the decay of an in-medium photon, which is it's still a relativistic, effectively particle. And so the dark matter that's getting born, because of conservation of energy and momentum, it's going to inherit those kinematic properties of its mother particle, right? So the dark matter is going to be born going very, very fast. And indeed, in this situation, you can actually compute in detail what is the phase space distribution of the dark matter being born this way. So what is the distribution of momenta that the dark matter has? And here, one thing to note is on the x-axis, I'm plotting the dark matter momentum in units of the photon temperature. And you can see that indeed, this is an order unity quantity for this distribution. So the dark matter is indeed going very, very fast when it's born. And at the same time, another point to note is that the dark matter clearly has a very non-thermal phase-space distribution, right? So it's very peaked at low momenta with this very, very fat tail. And that's in contrast to this green dashed line, which is the distribution that you would get had the dark matter been thermal. Now, it's possible that if dark matter can scatter with itself, it's possible for dark matter to thermalize through dark matter scattering. I want to emphasize that this is not meaning that the dark matter is thermalizing with the standard model. So those are still separate sectors. So dark matter would have its own temperature, but regardless of whether you have this purple distribution or whether you have this green dash distribution, in either case, there are going to be implications on cosmology from this phase-space distribution. And I just want to quickly go through what some of those are. One example of an implication is you're going to have some velocity effect on clustering. So some of you may have heard of warm dark matter. What that is it's just dark matter that gets born in the early universe in a way that's very similar to what the neutrinos are doing. So this is a dark matter particle, which was perhaps thermal in the early universe and decouples from the standard model bath while it's relativistic. And the amount of dark matter that you get, omega chi, you have this inverse relationship between m chi, the dark matter mass, and its temperature, T chi. So what I'm plotting here on the bottom panels is two simulations done assuming warm dark matter is all of the dark matter. You can see that the two simulations look very different if you make dark matter heavier or lighter. And what's going on here is that you have this trade-off. So if you make dark matter lighter, you have to crank up the temperature to get the same amount of dark matter at the end of the day. And if you have a low mass and a high temperature, that's very bad for cosmology because it means that your typical velocity, your RMS velocity, which is roughly the square root of T over M, is going to be very high. And that means that structure formation is not going to proceed as it ordinarily would because the velocity of these particles is so high that they're not able to be gravitationally captured by nascent cosmological structures that are trying to start to collapse and trying to form, right? So if you think about our universe, from what we observe, it seems to start out as a very smooth universe, and today it looks very clumpy. So it goes through this transition where it starts to coalesce and collapse and form these clumps. And while it's doing that, those clumps are very, very delicate, right? They can be easily perturbed. And if things that would have fallen into them are not falling into them, for example, if dark matter is just zipping by them and not being accreted, then that's going to disrupt their formation. And so that's why in these two pictures, on the right-hand side, you see that the lighter, hotter dark matter erases a lot of the structure and everything looks very much fuzzed out, particularly below a given length scale. So this type of effect is something that we're really great at looking for in cosmology. And one of the best probes that we have on this comes from the Lyman alpha forest. And so what's going on with this Lyman alpha forest is You start with some very, very distant, very high redshift quasar, which is just some source of broadband radio lines, which look something like this. So you have some spectrum, which intrinsically at the source looks like this. But then what happens is that over time, this light is traveling to our telescopes and it's moving through clumps of neutral hydrogen. And every time that the light passes through a clump, some Lyman alpha photons are absorbed by that gas. Now, as the photons are traveling, the whole universe is expanding, which means the whole spectrum is redshifting and moving to the right, which means that every time the light encounters a new clump of neutral hydrogen, there's some pristine part of the spectrum where Lyman alpha photons can then be absorbed. At the end of the day, what you end up with is this very dense so-called forest of spectral lines, and that tells you along the line of sight how many clumps of gas were there. So every one of those little absorption troughs corresponds to a clump of hydrogen. And from the wavelength of that absorption line, you know that it had to be Lyman alpha in the rest frame when that absorption was occurring. So you can infer from that how far away, at what redshift was this clump of hydrogen. And so along your line of sight, along this skewer that you're looking at, you know how much structure there is. And so you can look to see if there seems to be a lot of clumping or if some of that structure seems to have been erased. There's another type of effect that has gotten really good in recent years, and that is the formation of low mass halos and subhalos. So if you erase structure below a given scale, that also means that you're erasing the most fragile, the most delicate subhalos and halos of dark matter, which have the lowest mass and which would be the most easy to perturb and to smear out. And if we discover a lot of these low mass halos and subhalos, then that means that dark matter could not have been going very fast. Now, there's a bunch of methods we can use. We can use gravitational lensing. We can look for perturbations in very, very cold stellar streams, right? So if dark matter comes by a stellar stream, it can perturb the stream and mess it up. You can look for very faint nearby galaxies, or even in the future, you can use 21 centimeter cosmology to look for low mass halos. I'll just talk about the most, I think, concrete example of these points, which is just finding new dwarf galaxies, for example, with the Dark Energy Survey, which recently has found a ton more local dwarf galaxies, which are hosted inside of very, very low mass subhalos. And so the fact that all of these low mass subhalos exist means that the dark matter could not have been going too fast. So, okay, these are all great observational probes. What does that mean for dark matter freezing, making dark matter out of light? So going back to our friend, the phase-based distribution, there's two kinds of things to consider. On the one hand, if the dark matter is able to self-thermalize, if it's able to scatter with itself, then that means the dark matter must have a non-trivial speed of sound, and it cannot stream freely because it's interacting and bumping into itself. So that's something that you have to take into account when considering structure formation. On the other hand, if the dark matter is non-thermal, if it never thermalizes, if it's just the dark matter gets shot out of a cannon and never talks to anyone else, then in that case, you have to deal with this full non-thermal distribution. In particular, the high energy, high velocity tail of the distribution is what's responsible for doing most of the smearing. And you have to treat that kind of like the way we treat neutrinos in cosmology, which are also just these particles that are just free streaming through the universe. So in either one of these cases, we can take that into account in a Boltzmann solver like CLASS or Cmb. And so when you do that, what you find is that when you look at the power of structure formation relative to cold dark matter, on very, very large scales, you get agreement, you get as much power as you would get in cold dark matter. But on very, very small scales, we see that the power goes and drops to zero because structure is being erased. And it's very, very similar how that happens between warm dark matter, which I talked about, and freezing. Now, it's a little bit funny. So one thing to note is that the curves look a little bit similar, but the warm dark matter mass that I'm constraining or that I'm plotting here is actually lower than the freezing mass that I'm plotting. And that's just kind of a funky artifact. And it goes to show that physicists are terrible at naming things, because it turns out that freezing actually has hotter initial conditions than warm dark matter. And so that's why the curves look similar for actually a heavier freezing mass. But what we can do is when we compute this kind of effect on cosmology, we can take existing limits from warm dark matter, which is a very well-studied case, and we can directly apply them to freezing, provided some appropriate mapping. And so having done that, what we find is that the best constraint currently on freezing dark matter comes from these Dark Energy Survey satellites. And in detail, the constraint depends a little bit on whether the dark matter has thermalized or not. But roughly speaking, we can say that if dark matter were lighter than 17 keV, and if it were made by Friesen, then it would have erased some of these satellites, and so that's ruled out. Okay, with the last few minutes of my talk, I want to talk about another kind of effect, which we can use to look for Friesen. And I promised early on in my talk that I would return to tell you more about the CMB and what's going on with Cmb physics. So I'm going to tell you about that now, and I'm going to give you a very simplified kind of cartoon picture of what's happening here. So what's happening is that we have gravitational potential wells in the early universe, these small fluctuations in the metric or in the gravitational potential. And these are just initial seed fluctuations that we think are laid down in the very early universe by a theory like inflation, or insert your favorite theory here that does this. But regardless, there are these very small fluctuations in the gravitational potential. And again, because gravity is universal and it's attractive, everything wants to kind of fall in and cluster together inside of these gravitational potential wells. Now, with the photon baryon fluid, right, this is a plasma, it's tightly coupled. So on the one hand, you have gravity bringing things together, but at the same time, as I mentioned before, the fact that there's so many photons in our universe means that radiation pressure can become really important. And when you try to cram everything together, then radiation pressure can actually overcome the force of gravity and smear things out. And so you have gravity on the one hand pulling things together, you have radiation pressure smearing things out. Those are basically compressions and rarefactions. So you have all of the ingredients here in the early universe that you need for supporting a sound wave. And that's exactly what we see in the CMB when we look at these fluctuations. It turns out when you study the physics of that in detail, that corresponds to a sound wave. Now, at the same time, so that's what's happening with the photons and baryons, but at the same time, we have dark matter in the problem. And if dark matter is collisionless, and if it's not interacting very much with this primordial plasma, it does not feel radiation pressure. And so it's able to sink down to the bottom of the gravitational potential well. And in doing so, it's actually seeding structure formation for the photons and baryons. Because again, the fact that gravity is universal means that these photons and baryons feel the presence of the dark matter. So in the tipping point between gravity and radiation pressure, gravity actually has an advantage because of the presence of dark matter. And what that looks like in this picture is it looks like the compression parts of the spectrum look enhanced. And that's indeed what we find when we look at the CMB. We find that the compression parts are enhanced effectively because the dark matter is loading down, it's weighing down the baryons. And that's actually why we can precisely say exactly how much dark matter there is relative to ordinary matter. So that's the usual story with collisionless dark matter. On the other hand, though, in this scenario, because you're making dark matter out of light, that necessarily means the dark matter can talk to light just a little bit. So if that's the case, then the dark matter is essentially partly collisional. And every once in a while, a dark matter particle can be kicked out of the bottom of the gravitational potential well. And in doing so, that alters the CMB, because now the gravitational potential is not as steep as it would have been had the dark matter been collisionless. And so what that's doing is it's smearing things out even more. And that means that the compression peaks that you get are not as crisp, and neither are the rarefaction peaks, because everything is just more smeared out. And the effect that has on the CMB is to just reduce the amount of fluctuations that we see, because it's a smearing type of effect. And in particular, again, because I mentioned earlier on in my talk, because you have velocity to the -4 scattering, which is relevant for freeze in, that means that, again, our friend, the phase space distribution is going to play a critical role in determining exactly how this is going to happen. So let me just unpack that statement very quickly. If you look at these two distributions, what you see is that the peak of the distribution is markedly different. So if the dark matter does not thermalize, you have way more particles that are going slower, which means that the v to the -4 is going to be even bigger. So you're going to expect to see the most strong effect in the CMB if the dark matter is not thermal. And in particular, if the dark matter is completely cold, if it has temperature effectively 0, that is going to be the biggest possible effect that you could ever possibly hope to see. So given the couplings between the dark matter and the standard model that are relevant for freeze-in, how does this sort of behavior look? One way that you can kind of try to encapsulate it is as an effective drag rate between the dark matter and baryon fluids. Kind of similar to what I talked about earlier on in my talk with the bullet cluster, you can think about the two fluids dragging each other as they move through each other. And here on the y-axis, I'm plotting that in units of the Hubble rate. So this is a dimensionless quantity. And what you can see is that at times prior to recombination, so recombination happens at roughly redshift 10 to the 3. So prior to that, this drag rate in dimensionless units is roughly at the percent level. And in cosmology, and particularly with the CMB, we're able to do percent level science, make percent level statements all the time. That's become a relatively routine thing in the past couple of decades. And so what we can say is that we can try to actually look for this drag. And as you'll see plotted here, it does actually sensitively depend on whether the dark matter has thermalized or not. We see the smallest drag rate for the thermalized case because, again, most of the dark matter particles in the peak are going a little bit faster as compared to the non-thermal case. So the non-thermal case has a stronger drag rate. And the strongest drag rate of all is the cold initial conditions case. So what effect does this have on the acoustic peaks, the wiggles in the CMB? It looks something like this. The CLs are sort of the amplitude of these wiggles. So you can see that there's roughly a negative 0.5% effect on the CMB. That's a little bit scale dependent. And again, with the biggest effect coming from the cold initial conditions, and then the next strongest effect coming from non-thermal freeze-in. And then finally, the thermalized case is the weakest. Now, when we actually take this kind of a prediction and analyze Planck data, so Planck is a space-based telescope trying to look at the CMB in detail. When we take this prediction and match it with data, what we find is kind of funny, because from this picture, you would expect that the non-thermal freeze-in case would be a weaker, or would be a stronger constraint, excuse me, than the thermalized case. But in fact, we find the opposite. And the reason for that is because it turns out that going back to this picture, the way that the non-thermal freeze-in looks is actually a little bit degenerate with some cosmological parameters that are just vanilla cosmological parameters. So that degeneracy means that you weaken that kind of constraint. So the thermalized constraint is actually a little bit stronger. But again, regardless, so the details depend on the phase space, but regardless, it seems like freeze-in dark matter below 20 keV approximately is excluded by Planck. And in the future, we can actually do a lot better than this. So on the one hand, if we have CMB stage 4, which should be able to break a lot of the degeneracies that I mentioned, then we'll get to a situation where the non-thermal constraint will one day be stronger than the thermal constraint, and it'll be roughly in the ballpark of 30 keV. And thinking even more about other probes of structure formation, when we have Hera, which makes a detection of the 21 centimeter radiation from reionization, and also when we have the Vera Rubin Observatory, we're going to be able to constrain freeze-in up to even higher masses, going all the way up to almost roughly 100 keV. And one thing I want to really emphasize about this plot is, we have, several different kinds of astrophysical systems represented here, which are each independently giving their own constraint on this scenario. And that's actually really powerful. So the fact that, for example, let's say the Lyman alpha forest seems to be one of the weaker constraints. So you think, well, why even bother? But, astrophysical systems are messy, right? So perhaps you don't really think that you agree with one of the analyses of how, one of these groups analyzed their data. Perhaps you think that the assumptions that they made were not conservative, or, they were making too rigid assumptions. And that's perfectly, reasonable to question these analyses. But the point is that all of these different results are actually independent from one another. And so you can maybe nitpick with one analysis, but it's very difficult to nitpick with them all. And so we think, very robustly, actually, that dark matter freeze-in below roughly 15 keV is fairly safe to assume that it's excluded. And I also want to just come full circle and remind you that this entire shaded region is a key benchmark for direct detection experiments, which means that in a few years' time, we could be in a really great position where, on the one hand, we have constraints from astrophysics and cosmology constraining the freeze-in possibility from the masses coming from below. And at the same time, direct detection could be constraining masses coming from above. And we have a nice degree of overlap here between these two kinds of approaches, which means that in a few years' time, we could be in a situation where we've either not found anything, and in that case, we know that the freeze-in mechanism did not make this dark matter this way, or we could find something. So, one way or the other, we're going to know in a few years' time. And I think that's really exciting because this is the dark matter of our universe, right? So it's one thing to have a nice theoretical construct for how the dark matter could behave, but this is telling you about our universe. So I think that's really great. Okay, so I'll just really quickly summarize my talk. Dark matter could be made through this kind of freeze-in thermal-ish process, could be made of decaying light, an idea which sounds a little bit like an oxymoron, but as you've seen now, it's actually a key benchmark in direct detection experiments below the MeV mass scale, and it's actually the simplest way to make charged dark matter. As we saw, the non-thermal phase space distribution led to this really interesting cosmology. On the one hand, we had this warm dark matter style behavior, which was suppressing the formation of structure and smearing things out. And at the same time, we had this baryon dragging type of effect. And a final comment I want to make is that it's a really big universe. As we saw, there's a lot of complementarity between different independent types of astrophysical probes and a lot of room for creativity here. And the story that I told you earlier about the inspiration for this project is absolutely true, right? We were looking at something happening inside of stars. We were inspired by the interiors of stars, taking that example, porting it over to the early universe, the primordial plasma of our early universe, and then basically seeing all the ramifications that has throughout all the different astrophysical systems that we can observe. So, you know, I just want to leave a message for any students that might be listening that, you know, there's so many different astrophysical systems, so many theories of dark matter. We really need all the creativity and all hands on deck that we can muster. So if you're a student thinking about, you know, what kind of field to study, there's absolutely room for you in this type of field. So with that, I will end my talk and I'll take any questions now. Thank you.
Great. Thank you, Katelin, for a really fascinating and beautiful homecoming talk. And now we are ready. Maybe we should. And now we have some time for questions. So you can either raise your hands virtually, or you can even type the questions into chat and then we can get to those. So maybe I'll begin with asking a fairly general question. I'm curious, since dark matter can come in many different components, maybe a few, maybe even very many, and some of them might have more of a particle-like origin, reminiscent of what we see in the standard model. Some of them might be more gravitational. And my general question is, do we have any reliable quantitative estimates how much of dark matter has to come from some more or less traditional particle-like physics hidden sector, and how much of it can be purely gravitational modifications?
Great question. As far as I know, there aren't really any successful theories of modified gravity which simultaneously explain all of the observations. That's to my knowledge. So there are, of course, these like MOND type theories, modified Newtonian dynamics, which maybe work in some contexts, but don't work so great in others. So that's a little bit of a challenge. One nice thing about dark matter is that it's incredibly flexible, right? So just adding additional components of matter means that you can satisfy all of these various observations at the same time. So I'm not saying it's impossible for there to be modifications to gravity that can explain the dark matter, but I certainly haven't seen any examples that can explain every single thing. So with that being said, though, there's another angle to your question, which is that, well, maybe the dark matter is not made of particles. So one actually very compelling and rather trendy possibility in recent years is the idea that dark matter could be comprised of primordial black holes. This actually occurs in a lot of theories of inflation, for example, where you have multiple fields interacting during inflation. So that can happen pretty naturally. And the hunt is sort of on for those. It's been kind of a fun thing to see, different people over the past couple of years thinking of new ideas to try to look for these kinds of objects in our universe. So yeah, that's a very active area.
Great, thank you. I see Chris McKee has his hand up, so please, Chris.
Yes, so Katelin, I thought that was a great talk. My question is whether there'd be any possibility that these dark matter particles would interact with radiation inside stars. That is, as the particles try to go through a star, are there enough density of photons that they would interact and therefore accumulate in stars?
Yes, that is a possibility. So most of the examples that I know about are in situations where the dark matter is not interacting so much with the photons of the star, but more so with the dense nuclear matter inside of the star. And indeed, yeah, in some theories of dark matter, the dark matter can accumulate very efficiently. both through just scattering with dense nuclear matter as the star is like sweeping through the galaxy, as well as through gravitational focusing types of effects. So maybe the dark matter scatters, its orbit is perturbed, and then the fact that you have gravity of the star, which is very, very strong, can also be efficient at trapping dark matter particles. So in some contexts, for some theories of dark matter, that actually can be a very important way of constraining that theory. Yes.
Yeah, and what about in the theory you talked about today?
Yeah, so unfortunately, the answer is no. The coupling is just a little bit too weak between the dark matter and the photons in this case. Yeah, so it's 10 to the minus, so the charge is 10 to the minus 10, 10 to the minus 11, which means any process has to be at least of order charge squared, so 10 to the minus 22. It's a pretty small number, yeah, so it's hard to overcome that. You really need a very, precision type of experiment to try to look for that.
Okay, any other questions? I don't see any raised hands at this point, and I don't see anything new in the chat, so please feel free to ask.
Hello, I have a question.
Okay.
I couldn't figure out how to raise my hand here. I know you covered this, but if you could remind me, what is the process of light decaying into dark matter? You mentioned it could be, photons could decay.
Yeah,
Okay.
that's right. Yeah, so inside of a dense medium, photons effectively have an in-medium mass. Their dispersion relations are altered. I actually think I have a plot of these dispersion relations here. So this is what they look like inside of a medium. So this, I'm showing the dispersion relations for the photon that's inside of a relativistic plasma of temperature 1 MeV. So you can see that both the transverse and longitudinal modes both have a finite mass. Which, by the way, in a vacuum, the photon doesn't have a longitudinal mode, but inside of a medium, it does. And so because it has all this phase space now, it has this effective mass, you can have plasmons that decay to particles, provided that they're sufficiently light and weakly coupled. Now, for example, you might wonder, well, could this type of process, whoops, I'm trying to scroll back here to my previous plot. You might wonder, could this type of process, could plasmons decay to electrons and positrons? And the answer turns out to be no, because even if the plasma mass is high enough, electrons and positrons also have a coupling to the plasma. And so that means that their effective mass also goes up. And it turns out that kinematically, the effective mass of the electrons and positrons always goes up faster than the effective mass of the photons. And so it's never kinematically allowed. So really the only particles that you can decay to through this kind of process are the very light weakly coupled ones. So in the standard model, that would be the neutrinos. But now what we're saying is, well, if you have dark matter that's very light and very weakly coupled, this could be another process that could be relevant. Yeah.
Okay, thank you so much.
All right. Thank you very much. Any other questions from anyone? I don't see any raised hands or chat questions. So perhaps we should thank Katelin again for the wonderful talk.
Thank you, Katelin.
It's always great to have you back in Berkeley, even if it has to happen only virtually. So hopefully next time it will be again in person, not too far in the future.
I hope so.
Thank you again.
Thanks.
All right. Stay safe.